With any new design, always challenge your assumptions. Right now, we want to verify the non-blocking nature of the WebSocket protocol within the context of our implementation. We can do this by simulating a long-running activity in order to observe how it affects data flow over the WebSocket pipeline. Let's modify the index client.js file like so. I add a non-blocking function to mimic a long-running process by any specified number of seconds. We intend to trigger the function repeatedly over our WebSocket connection and observe whether the responses inadvertently become serialized. The next bit of code here happens when we receive data request from the WebSocket source. I check if the request data is for item 3, and then use the mimic function to stall 3 seconds before returning a response. Let's run the modified program. As I click to select the items on the list, the responses over WebSocket plays out. You can see the response for item 3 takes longer than others, but do not get in their way. This tells us that the WebSocket delivery mechanism is managing the flow of data asynchronously, as we expect. However, it's noted we don't know how much payload data, nor the number of concurrent requests, could be a limiting factor here. Next, we want to verify whether the socket I/O acknowledgement is sound, meaning the responses to asynchronous requests are being fulfilled correctly and no request receives a response intended for another. We will be modifying both client and server files, beginning with indexserver.js. I add a reference to the Hexoid utility module, which helps to generate a random ID. You'll need to install this module into your project before use. The aim here is to tag every message to be sent over WebSocket with its own unique ID. Then check against the ID returned by the WebSocket response. An exact match is what we're expecting. I'll scroll to the function that receives the user request for item details. Remember, this is the function that is triggered when a user posts from a web form. First, generate a random ID string for every incoming request. Include the generated ID next to the existing content to be sent to the socket I/O client. Later on, I will update the socket I/O client code to return the received ID in the acknowledgement message. If all goes well, we should be accessing the same ID in the acknowledgement. Here, I compare the echoed ID with the original ID, and if not matching, log a message to the terminal. Let's now modify the index client.js file. I'll replace the existing sleep delay routine with one based on a more random timing. This will create a mixture of responses, some that don't go in sequence with incoming requests. I recall we need to return the request ID back to the sender. This completes the modification. Let's run the modified program. As I rapidly click to trigger multiple requests and responses across the WebSocket pipeline, I'm also watching the index server terminal and don't see any failing checks on non-matching message IDs. Finally, we want to verify whether the socket I/O client is able to operate in a machine that does not allow any inbound connection. To test this out, I make use of Docker virtualization to isolate the socket I/O client runtime. I duplicate the index client codes in a new Node.js project, build the image using default Docker settings, and run the container package using Docker Desktop on Windows. This is all standard Docker stuff. However, one important thing to note is we will need to modify the reference to localhost in the index-client.js file. Let's take a look. Instead of localhost, we change it to host.docker.internal. This special DNS name allows the socket IO client to reach the host machine from the container. And that's it. We run the index client container in Docker and run the index server on Windows as normal, then use the browser to verify everything still works. In the next video, we'll take a look at load balancing to improve performance.